If a storm that can snap utility poles the way you'd snap a dry twig for 800 miles without stopping, without weakening, has you as locked in as it has me, hit like and subscribe to Signal Watch so you don't miss a single update as we track these systems. Drop a comment below telling us where you're watching from, what time it is there, and this. Have you ever been caught in a derecho? Did you even know what hit you while it was happening? If you want to help this community keep growing, share this video on X, Facebook, Reddit, or just drop it in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Now, here's what we're going to unpack today. A cold front moving at highway speeds, violently colliding with a corridor of tropical moisture, and the chain reaction that turns that collision into a self-sustaining wall of destruction 800 miles wide. The physics of the rear inflow jet, the hidden engine inside these storms that scientists at the Storm Prediction Center describe as momentum transfer from the upper atmosphere directly to the ground. The day in August 2020 when one of these systems made landfall across Iowa and tore through Cedar Rapids with estimated wind gusts of 140 miles per hour, and the $11 billion of damage that made it the costliest thunderstorm event in recorded American history. And the reason the power grid, the crops, the trees, the cell towers, none of it is built to withstand what these storms are capable of delivering in a single afternoon. Now, settle in and let's get into it.
There is a category of severe weather in America that kills more people per year than tornadoes, costs more per event than most hurricanes, and does it all without a name. Hurricanes get names. They get press conferences. They get days of buildup and evacuation orders and satellite tracking on every cable news channel. Tornadoes get sirens and wall-to-wall radar coverage and the kind of breathless live television that stops normal programming entirely. But a quasi-linear convective system, a QLCS, capable of generating a serial derecho? You might get a severe thunderstorm watch at noon, and by 3 in the afternoon, you're standing in the ruins of your neighborhood wondering what just happened. That asymmetry between threat and public awareness is the story. And it starts with a fundamental question about physics. When a cold front smashes into a corridor of Gulf moisture over the Great Plains, not a gentle interaction, not a gradual mixing of air masses, but a violent, high-speed collision between two utterly incompatible atmospheric states, what happens at the boundary? What happens along that front line where cold, dense air is bulldozing southward at 40 or 50 miles per hour into warm, humid air that is already loaded with convective available potential energy, CAPE, measured in the thousands of joules per kilogram? What happens is that the atmosphere becomes a pressure cooker with the lid about to blow. And it doesn't blow in one place. It blows in a line. The National Oceanic and Atmospheric Administration's Storm Prediction Center, based in Norman, Oklahoma, defines a derecho as a windstorm associated with a mesoscale convective system that produces a swath of wind damage at least 250 miles long, with gusts of at least 58 miles per hour along its length, and several well-separated gusts of at least 75 miles per hour. That is the minimum standard for the name. That is what earns the classification. But a serial derecho, the specific and more dangerous subspecies that concerns us today, isn't a single bow-shaped storm. A serial derecho is an entire squall line containing multiple bow echoes simultaneously, each one generating its own rear inflow jet, its own downburst clusters, its own families of mesovortices spinning up along the leading edge. It is not one storm that bows out and races east. It is a continuous, unbroken wall, potentially 800 miles of it, where every 20 or 30 miles there is another bow, another rear inflow jet dragging upper-level winds down to the surface, another burst of straight-line winds that can reach 100, 110, 120 miles per hour without warning. The Storm Prediction Center's own glossary describes serial derechos as an extensive squall line in which a series of line echo wave patterns and bow echoes move along the line. What that clinical description doesn't capture is what it looks like on radar. It looks like a continent bowing inward, like the atmosphere itself is pressing its fist against the eastern half of the country, and it moves fast. Highway fast. The August 10th, 2020 event moved at approximately 55 miles per hour. At that speed, a system that initiates in eastern Nebraska before sunrise is carving through Cedar Rapids, Iowa by midday, and reaching northern Illinois and southern Wisconsin by mid-afternoon. You have hours, sometimes less. The public awareness gap is real, and it is dangerous. A tornado warning triggers an immediate, visceral behavioral response: shelter, basement, underpass. A severe thunderstorm warning, which is all a QLCS passage initially produces in many affected counties, triggers almost nothing for most people. They watch the radar on their phone. They see a line of storms. They think, it'll pass in 20 minutes. They're right about the 20 minutes. What they're wrong about is what 20 minutes of 100 mile per hour straight line winds does to a power grid, a neighborhood, a city's tree canopy, a county's corn crop. What it does is erase it. Not every severe thunderstorm outbreak produces a serial derecho. The atmospheric conditions that allow a continuous 800-mile squall line to not only form, but to sustain itself for 12 to 14 hours while racing across multiple states. That combination is specific. It is knowable. And when meteorologists see it coming together on the models, the ones who have studied these systems know exactly what that combination means. The recipe has 4 essential ingredients. Remove any one of them, and you get a severe thunderstorm outbreak, maybe an isolated bow echo, maybe some wind damage, and a few power outages. Put all 4 together in the right configuration, and you build the planetary plow. The first ingredient is instability, and not mild instability, but extreme atmospheric instability, measured as convective available potential energy. Research published in the American Meteorological Society journals on the large-scale environments associated with derecho initiation found that compared to non-derecho, mesoscale convective systems, derechos form in environments with measurably larger CAPE, steeper lapse rates between 850 and 250 hectopascals, and higher low-level specific humidity. That last factor, the moisture, is where the Gulf of Mexico enters the story. The North American continent has a design feature that exists nowhere else on Earth at this scale. The Rocky Mountains run north to south, not east to west. There is no natural barrier between the Gulf of Mexico and the Canadian border. Nothing stops warm, moisture-laden air from the Gulf, air carrying dew point temperatures in the upper 60s or low 70s Fahrenheit, from flowing northward across the flat terrain of Kansas, Nebraska, Iowa, Illinois. The low-level jet stream, which typically peaks in strength overnight and in the early morning hours, acts as a river in the lower atmosphere, pumping Gulf moisture directly into the collision zone ahead of an advancing cold front. When dew point temperatures ahead of the cold front are sitting at 68, 69, 70 degrees Fahrenheit across a corridor that is 500 miles wide, the potential energy stored in that air column is staggering. Surface-based CAPE values in a prime derecho environment can reach 2,000 to 3,000 joules per kilogram. In exceptional cases, the kind of case that produces an event like August 10th, 2020, CAPE can approach 4,000 joules per kilogram across a broad swath. For context, significant tornado outbreaks often occur with CAPE values of around 1,500 joules per kilogram. The energy available in a prime serial derecho setup is roughly double that. The second ingredient is wind shear. Specifically, the difference in wind speed and direction between the surface and the middle and upper levels of the atmosphere. Wind shear is what organizes convection. Without it, thunderstorms grow straight up and collapse back down. With it, they tilt. That tilt is what separates a garden variety severe thunderstorm from a storm that can sustain itself for 14 hours across 770 miles. In the upper levels, the jet stream layer, at 30,000 to 40,000 feet, winds during a prime derecho setup are typically roaring at 60 to 80 knots from the southwest or west-southwest. At the surface, ahead of the cold front, the winds are southerly at 15 to 25 knots. That enormous difference in speed and direction over a vertical distance of roughly 6 miles creates the conditions for the bow echo to develop and sustain itself. The tilted updraft of the storm draws in the jet stream winds, which spiral down through the storm system and emerge at the surface as the rear inflow jet, the hidden engine that drives the most destructive winds. The third ingredient is the cold front itself, specifically a fast-moving cold front with a steep temperature gradient. Not all cold fronts produce severe weather. A slow-moving front that inches eastward over 2 or 3 days gives the warm sector ahead of it time to mix, stabilize, and dissipate its potential energy. A fast-moving cold front that advances 40 to 50 miles per hour is a different animal entirely. It is a forcing mechanism. It is the match being dragged across the strike plate of an atmosphere that has been loaded for hours with Gulf moisture and solar heating. When that fast-moving cold front collides with the warm, unstable air ahead of it, it doesn't slide gently underneath it. It bulldozes into it. The cold, dense air drives under the warm air like a wedge, forcing it upward at a rate that can trigger explosive convective initiation, the meteorological term for what ordinary people would call a line of violent thunderstorms erupting essentially simultaneously along the frontal boundary. The fourth ingredient is what meteorologists call a permissive upper-level pattern, usually a deep trough in the northwestern United States, with diverging flow in the upper troposphere over the region where the storms are developing. That upper-level divergence acts as a lid removal mechanism, helping lift the cap of stable air that would otherwise suppress convection, and then drawing the developing storms upward and organizing their outflow in the direction of storm motion. When the Storm Prediction Center sees these 4 factors aligned, extreme CAPE, high low-level specific humidity from Gulf, moisture advection, fast-moving cold front, and a deep upper-level trough with divergent flow, what they see on the outlook map is not a scattered severe weather threat. What they see is the potential for a high-end wind event, the kind where the discussion notes include language like, a corridor of particularly intense wind damage is possible, and forward speeds of the convective system will be high. That language is the tell. That's the signal that what is being discussed is not a severe thunderstorm outbreak. What is being discussed is a wall. To understand why a serial derecho is so much more dangerous than its ingredients suggest, you have to understand what happens inside an individual bow echo, and then understand what happens when you chain 50 of them together in a continuous line. A bow echo begins as a cluster of thunderstorms. It doesn't announce itself as a bow echo. It starts as convective initiation along the frontal boundary, anvil-top thunderstorms erupting upward through 50,000 feet, drawing warm, moist air in at the base and expelling it through the anvil at the top. This is ordinary thunderstorm behavior, but in the environment we described in Part 2, high CAPE, strong wind shear, fast-moving forcing mechanism, something different happens in the mid-levels of the storm. Rain-cooled air from the storm's downdraft hits the ground and spreads outward. That cold air is dense. It hugs the surface and races ahead of the storm system as what meteorologists call the gust front. The gust front is the leading edge of the cold pool, the wedge of rain-cooled air that has descended from the storm and is now plowing forward at the surface. When you feel the sudden temperature drop and wind shift just before a severe thunderstorm arrives, you are feeling the gust front. You are standing at the leading edge of the cold pool. Here is where the physics of the bow echo becomes remarkable. As the cold pool expands and the gust front races ahead of the storm, it undercuts the storm's warm sector inflow. The updrafts, the rising columns of warm, moist air that are powering the storm, get tilted back by the gust front. The storm reorganizes around this tilt, with the updraft leaning back over the cold pool and the downdraft churning down through the back of the system. In the mid-levels of the atmosphere, behind the leading convective line, something crucial is forming. The storm has created a mesolow, a small area of mid-level low pressure. In its stratiform rain region, that low pressure draws air in from the rear of the storm. This is the rear inflow jet. Air from 50 or 100 miles behind the leading edge of the storm is being pulled inward at the mid-levels and then descending steeply as it approaches the front of the system. According to the National Oceanic and Atmospheric Administration's Bow Echo guidance, the rear inflow jet forms as air, is drawn in under the trailing stratiform region of precipitation. Before reaching the leading edge, the jet descends to the surface as a strong downdraft, creating straight-line winds. In a mature, well-organized bow echo, the system relative rear inflow can exceed 38 meters per second, that is approximately 85 miles per hour. That air, once it descends and hits the surface, becomes the damaging wind event. But that is the rear inflow jet in isolation. In a serial derecho, the rear inflow jet is not isolated. Every bowed segment of the 800-mile squall line is developing its own rear inflow jet simultaneously. The NOAA and Navy Research Laboratory P-3 aircraft that flew into squall lines during the Bow Echo and Mesoscale Convective Vortex Experiment, BOMEX, documented rear inflow jet strengthening to 17 meters per second that was concurrent with the formation of a bow echo and two counter-rotating vortices at either end of the bow. Those counter-rotating vortices at the ends of the bow, called bookend vortices, are where some of the most extreme and concentrated wind damage occurs. Along the leading edge of the bow, smaller circulations called mesovortices spin up. In the June 30th, 2014 event over northern Illinois and Indiana, a serial derecho event in its own right, researchers documented 38 mesovortices associated with the second quasi-linear convective system, with up to 15 mesovortices ongoing simultaneously. These mesovortices are not tornadoes in the traditional sense. They are tornado-scale circulations embedded within the larger wind damage swath, capable of producing damage indistinguishable from a weak tornado, but occurring along a line dozens of miles long, rather than a narrow path a few hundred yards wide. The result is a damage signature that is fundamentally different from a tornado outbreak. A tornado path is narrow, hundreds of yards. An individual mesovortex within a bow echo can be a quarter-mile wide. The rear inflow jet wind damage swath can be 5 to 10 miles wide. The full damaging wind corridor of an 800-mile serial derecho can be 100 miles wide in places, with straight-line wind damage covering every square mile of that corridor. This is the planetary plow, not a scalpel, a blade. On August 10th, 2020, at approximately 5:30 in the morning local time, a line of thunderstorms began developing near the South Dakota and northeastern Nebraska border. The Storm Prediction Center had issued a high risk of severe weather, their highest categorical outlook, for portions of Iowa and surrounding states. The models had been consistent. The environment was primed. Extremely high CAPE values, dew point temperatures in the upper 60s across the warm sector, a fast-moving cold front, and a deep upper-level trough positioned over the northwestern United States. By the time most people in Cedar Rapids, Iowa woke up that Monday morning, the system was already intensifying over central Iowa. A prominent bow echo had formed on NEXRAD radar. The National Weather Service office in Des Moines was issuing tornado warnings as embedded mesovortices spun up along the leading edge. The system moved at approximately 55 miles per hour. It was not possible to outrun it by car. By the time you could see it coming on radar, it was already upon you. The 2020 Midwest derecho lasted 14 hours from initiation to final dissipation. Its track length was 770 miles, from southeastern South Dakota and northeastern Nebraska, through Iowa, across northern Illinois and southern Wisconsin, through northern Indiana, southwestern Michigan, and into northwestern Ohio. It covered 90,000 square miles of American territory. What it left behind redefined the benchmark for what a mesoscale convective system can do to a populated landscape. In Cedar Rapids, Iowa, a city of approximately 140,000 people, the National Weather Service estimated peak wind gusts of 140 miles per hour. Let that land. Not 90 miles per hour, not 100, 140. That is Category 4 hurricane wind speed. It is the wind speed at which roof decks begin to fail on well-constructed homes. It is the wind speed at which well-established trees don't just snap, they are extracted from the ground. Cedar Rapids, with its mature urban forest of hundreds of thousands of trees, was eviscerated. According to the Iowa Department of Natural Resources, nearly 2.67 million trees were killed or damaged across the state during the derecho. In the Cedar Rapids and Marion area alone, 50 to 65% of the tree canopy was destroyed. In the most severely affected neighborhoods, 75% of the canopy was gone. 669,000 trees in Cedar Rapids alone were destroyed. Trees that had grown for decades. Trees that shaded streets, cooled neighborhoods, absorbed stormwater. Gone in 40 minutes. The power grid was no match. More than 1.9 million homes and businesses across the affected states lost power. In Iowa alone, 480,000 customers were without power immediately after the storm. Some of those customers, in the most severely damaged portions of the grid, were without power for 2 weeks, not 2 days. 2 weeks. The crops took losses that are almost incomprehensible in scale. The USDA estimated that 850,000 acres of corn and soybean crops across Iowa were a complete loss. The August timing was deliberately cruel. This was not crops that could be replanted. This was corn within weeks of harvest, corn that had spent the entire growing season accumulating the carbohydrate reserves that made it worth harvesting. The derecho hit at the moment of maximum vulnerability, and the entire output of nearly 1 million acres of Iowa farmland simply disappeared. The total damage reached $11.2 billion. The National Oceanic and Atmospheric Administration confirmed it as the costliest thunderstorm event in the recorded history of the United States. Not the costliest derecho, the costliest thunderstorm event. Period. Hurricane Laura, which struck the Gulf Coast in August of that same year, caused approximately $14 billion in damage. The August 10th, 2020 derecho came within striking distance of a landfalling major hurricane's damage total. 4 people died. That number is both the tragedy and, in a different sense, the undercount of what the storm meant. Because what the August 10th, 2020 event demonstrated, definitively, with $11 billion of evidence, is that the infrastructure of an entire region cannot withstand what a fully developed serial derecho delivers in a single afternoon. And it demonstrated something equally important, that the warning system as it existed was not built for an event that moves this fast, hits this hard, and covers this much territory simultaneously. The August 2020 event was the worst of its kind in recorded history, but it was not the first. Serial derechos have been recorded in American meteorological literature for more than a century, and the pattern they follow is consistent enough that researchers at the Storm Prediction Center have assembled a detailed climatology of their occurrence. The term derecho itself is not new. It was coined by Dr. Gustavus Hinrichs of the Iowa Weather Service in 1888, specifically to describe the straight-line wind damage from a convective windstorm that moved across Iowa. Hinrichs chose the Spanish word for straight, contrasting it with the Spanish word for left, which he had been using to describe tornadic winds. 137 years after Hinrichs first described the phenomenon from an Iowa summer, the costliest event in the history of the classification hit. Also in Iowa. Also in summer, also with unprecedented straight-line winds. The historical record of major American derecho events reads like a catalog of infrastructure disasters. The June 29, 2012, Mid-Atlantic and Ohio Valley derecho, sometimes called the North American derecho of 2012, swept from Indiana to the Atlantic coast in one night. It knocked out power to 4.2 million customers across 11 states and Washington, D.C. It killed 22 people. Temperatures in the affected region the following week climbed above 100 degrees Fahrenheit, and the combination of extreme heat and no power resulted in cascading health emergencies across the Mid-Atlantic. The June 30, 2014 event over northern Illinois and Indiana produced 2 successive quasi-linear convective systems in 7 hours, the second of which generated 29 confirmed tornadoes and estimated straight-line wind gusts of 80 to 100 miles per hour. Researchers at Iowa State University documented 38 mesovortices occurring along the system's leading edge during the second event, an extraordinary concentration of embedded circulations that produced damage patterns virtually indistinguishable from a tornado outbreak. The April 4th and 5th, 2011 event extended more than 1,000 kilometers from the Ohio River southward to the Gulf Coast and produced a record 1,096 non-duplicate damaging wind reports in a single 24-hour period, along with nearly 4 dozen tornadoes. The Storm Prediction Center's analysis published in the scientific literature called it an expansive quasi-linear convective system accompanied by a broad swath of strong winds. 1,096 wind damage reports in 24 hours. Ashley and Moat's foundational research, published in the American Meteorological Society literature, established that approximately 20.9 derecho events occur across the United States each year, accounting on average for $95.7 million in damage per event and 8.5 fatalities and 144.7 injuries annually. That baseline, established from data through the early 2000s, has been stress-tested repeatedly by events that far exceed the statistical average. What the historical record shows is not that serial derechos are rare. What it shows is that the extreme end of the distribution, the $11 billion event, the 4.2 million customer power failure event, is more accessible than the baseline statistics suggest, because the baseline statistics include all 20-odd annual events, most of which are modest. The outliers, the ones that match the atmospheric setup we described in Part 2 in every particular, are what define what these systems are truly capable of. And the atmospheric setups that produce the outliers are produced by the same basic geography and the same basic thermodynamic machinery that has always existed over the American interior.
The Gulf moisture is still there. The Rockies still run north-south. The Canadian air masses still have an unobstructed path to the Gulf Coast. The jet stream still creates the shear that organizes these systems. None of those fundamentals have changed.
To truly understand what a serial derecho looks like in its mature phase, when it has been running for 6 or 8 hours, when every component of its internal machinery is working at full capacity, when the rear inflow jet is fully established and the bow echoes are stacking along the line at irregular intervals, you have to understand how weather radar reads it. The WSR-88D Doppler radar network, the NEXRAD network, is the primary observational tool for diagnosing these systems in real time. There are 160 radar stations in the continental United States, each one scanning the atmosphere at multiple elevation angles every 4 to 5 minutes in standard mode and as frequently as every 60 seconds in severe weather mode. When a mature serial derecho is moving across the NEXRAD coverage area, the radar picture is unmistakable. The reflectivity image, the one most people associate with weather radar, the image that shows precipitation intensity in colors from green through red, shows a continuous line of high reflectivity echoes stretching for hundreds of miles. Red and purple colors denote reflectivities above 60 decibels of Z, the equivalent of extremely heavy rain or large hail. Along the leading edge of a serial derecho, this high reflectivity line is nearly unbroken, and at intervals along it, you can see the individual bowing segments, arcs where the leading convective line has pushed forward faster than the surrounding line sections, creating the characteristic bow shape that gives the bow echo its name. But the reflectivity image only tells part of the story. The velocity image, the Doppler radial velocity product, tells the rest. In radial velocity, the radar measures how fast precipitation is moving directly toward or away from the radar beam. In a bow echo, the velocity signature is dramatic. At the apex of the bow, where the rear inflow jet is delivering its fastest winds to the surface, the velocity colors go from vivid green on one side, winds rushing toward the radar, to vivid red on the other side, winds rushing away. This abrupt color transition, called a couplet in radar terminology, can indicate the location of the most intense surface winds and embedded mesovortices. During the August 10th, 2020 event, the radar operators at the National Weather Service office in Des Moines and at the Davenport, Iowa radar site, we're watching velocity couplets of extraordinary intensity develop as the system moved through central Iowa. The measured radial velocities, which represent only the component of the wind, moving directly toward or away from the radar beam, not the full wind speed, were reaching values associated with estimated surface wind gusts well above 100 miles per hour. The inflow notches visible in the reflectivity data, where the bow echo was drawing in surface air with unusual ferocity, were co-located with those velocity couplets. The NEXRAD data from the August 10th event documented something specific that underscores the systemic danger of this type of storm. The bow echo that produced the most extreme winds in Cedar Rapids didn't announce itself with gradually increasing radar signatures. It intensified rapidly. What meteorologists call a bow echo undergoing rapid intensification in the 20 to 30 minutes before it arrived over the most densely populated portions of the city. The lead time between the first indication of the extreme wind signature and the arrival of those winds at the surface was, in some portions of the Cedar Rapids metropolitan area, less than 15 minutes. The National Weather Service storm survey teams that moved through Cedar Rapids in the days following the storm found damage consistent with those wind estimates. Apartment complexes along Wilson Avenue and Wiley Boulevard in southwest Cedar Rapids had been demolished. Entire sections of exterior wall were missing. Semi-trucks on Interstate 380 had been overturned. The National Weather Service estimate for those areas was 140 miles per hour, and the damage patterns they documented were consistent with that estimate. The University of Iowa campus in Iowa City, roughly 30 miles south of Cedar Rapids, sustained damage rated consistent with 80 to 90 mile per hour gusts. Illinois had multiple sites with gusts recorded by automated surface observing systems above 80 miles per hour. The damage corridor was real, it was measurable, and it was continuous. This is the signature of the mature serial derecho on NEXRAD, an unbroken line of red and purple reflectivity, interrupted at regular intervals by the bowing signatures of individual bow echoes, each one flagged with a velocity couplet that quantifies the rear inflow jet's surface impact, each one capable of delivering winds that dwarf the warning thresholds that govern the National Weather Service's severe thunderstorm warning criteria. If you ask the average American what drives the destructive winds in a severe thunderstorm, they'll tell you about downdrafts. They're not wrong. Downdrafts, columns of cold, dense air descending from the storm and hitting the surface, are real and they are destructive. A microburst, which is an intense, localized downdraft, can generate winds of 100 miles per hour or more directly beneath the storm. But the rear inflow jet is something different. And in a fully mature bow echo, or serial derecho, it is the mechanism responsible for the most widespread and sustained damage. Here is how it works at the physical level. As a bow echo matures, it develops a stratiform precipitation region behind the leading convective line, the trailing region of lighter, widespread rain and ice crystals that extends back 50 to 100 miles from the front of the storm. Within this stratiform region, precipitation is falling and evaporating. That evaporation cools the air. In the mid-levels of the atmosphere, roughly 10,000 to 15,000 feet, this cooling creates a small but significant area of low pressure, the mesolow. The mesolow draws air inward. Because of the geometry of the storm system, the leading convective line is ahead, the stratiform region is behind. The air being drawn inward by the mesolow comes from the rear. It enters from behind the storm at the mid-levels, flowing forward under the trailing staff stratiform cloud deck. And as it flows forward toward the convective line, it begins to descend. It descends because it is approaching the strongest updrafts in the system, the tilted, rearward-leaning updraft cores of the leading convective cells, and the dynamic pressure gradient between the mid-level mesolow behind and the updraft cores ahead forces the air downward. As it descends through the middle and lower troposphere, it accelerates. By the time it reaches the surface, after descending from 10 or 12,000 feet, it has been accelerating for potentially 30 or 40 miles of horizontal travel. It hits the surface as a sustained, broad current of destructive wind. Research from the Bow Echo and Mesoscale Convective Vortex Experiment. BAMEX, the field campaign that put NOAA and Navy Research Laboratory P-3 research aircraft directly into bow echoes over the Great Plains and Midwest, documented rear inflow jet speeds of 17 meters per second system relative. In one case study from June 29, 2003. 17 meters per second system relative means that the air is flowing toward the convective line at 17 meters per second in the storm's own reference frame. In ground relative terms, the speeds that damage things on the surface, the contribution of the rear inflow jet to surface wind speeds can push damaging winds to the 70 to 100 mile per hour range, even in storms that would not otherwise reach those speeds based on convective updraft and downdraft dynamics alone. The BAMEX research also documented the timing of the rear inflow jet's development relative to the bow echo. The strengthening of the system relative rear inflow to 17 meters per second was concurrent with the formation of a bow echo, an increased dynamic pressure gradient beneath the rearward tilted updraft, and two counter-rotating bookend vortices at either end of the bow. This tells us something critically important about the feedback loop. The bow echo and the rear inflow jet co-evolve. They strengthen each other. A stronger bow echo generates a stronger mesilo, which draws in a stronger rear inflow jet, which pushes the leading edge of the cold pool forward faster, which intensifies the bowing, which strengthens the mesilo. This is a self-amplifying system. This is why a serial derecho, once established in a favorable environment, can sustain itself for 14 hours across 700 miles without significant weakening until it runs out of instability. In a serial derecho, this self-amplifying feedback loop is not operating in one place. It is operating in every bowed segment of the 800-mile line simultaneously. Each individual bow has its own rear inflow jet. Each one is drawing mid-level air down to the surface, and because the individual bow echoes are embedded in a larger continuous squall line, the overall system dynamics reinforce each individual component. The mesovortices that form along the leading edge of each bow, the rotating circulations that can generate embedded intense wind damage, are in part products of the bookend vortices at either end of each bow, interacting with the surface cold pool boundary. When the rear inflow jet impinges on the gust front, it generates horizontal vorticity along the boundary. That horizontal vorticity can be tilted into the vertical by the storm's updraft, creating the mesovortex signature. In the June 30th, 2014 Illinois and Indiana event, researchers documented 15 mesovortices active simultaneously, the equivalent of 15 simultaneous embedded circulations generating tornado-like damage patterns along the leading edge of a single system. The critical implication is this: the severe wind threat from a serial derecho is not a point threat. It is not even a narrow corridor threat, the way a tornado is. It is an aerial threat, a damage swath potentially 100 miles wide and 800 miles long, with the most intense embedded features impossible to predict with precision more than minutes before they arrive. The American electrical grid was not built to withstand this, and that is not an accident of negligence. It is a function of engineering, economics, regulatory philosophy, and a design assumption that was reasonable at the time it was made. Most of the distribution infrastructure that moves electricity from high-voltage transmission substations to individual homes and businesses, the poles and wires that line every residential street and rural road in the country, was designed and built to withstand winds of approximately 90 miles per hour. That design standard, set by the National Electrical Safety Code, reflects a level of engineering conservatism appropriate for the expected wind environment in most of the country. The expected wind environment, as understood when much of this infrastructure was built in the middle of the 20th century, did not adequately account for the extreme tail of the wind distribution, the mesovortex embedded within a serial derecho that delivers 120 or 140 miles per hour straight-line winds to a path 5 miles wide for 20 minutes straight. At 90 miles per hour, a well-designed wooden utility pole can survive. At 110 miles per hour, the failure probability rises sharply. At 120 miles per hour, sustained over 5 to 10 minutes, the failure rate is very high. At 140 miles per hour, the estimated PU gusts in Cedar Rapids on August 10th, 2020, wooden utility poles don't lean. They snap. They snap at the base, where decades of ground moisture have weakened the wood, or they snap mid-shaft, where the bending moment from the wind force exceeds the wood's structural capacity. And when they snap, they take everything with them: the wires, the transformers, the neighborhood level service connections. According to research published by the Union of Concerned Scientists reviewing major power outages across the Midwestern Independent System Operator Territory between 2014 and 2024, summer derechos led to 3 of the 10 worst outage days in a decade-long record. The August 10th, 2020 derecho left nearly 1.7 million customers without power at its peak. The 70% of American power outages that originate at the distribution level, at the poles and wires along streets, not the high-voltage transmission towers, are almost entirely caused by weather, and the combination of tree failure and pole failure during extreme wind events is the dominant mechanism. The August 2020 aftermath in Cedar Rapids illustrates the cascading geometry of the grid failure. When a utility pole snaps, it falls across the wire below it or across the wire it was supporting. That wire, now earthed, creates a safety hazard. The circuit it was part of trips at the substation, an automatic protection mechanism that prevents electrocution and equipment damage. The substation now has one feeder circuit off. But because the August 10th, 2020 event produced pole failures across hundreds of linear miles of distribution circuits simultaneously, the substations weren't losing one feeder. They were losing multiple feeders in rapid succession. The automated restoration systems that utilities rely on to re-energize circuits after brief faults were encountering physical damage, broken poles, fallen transformers that prevented re-energization entirely. Repair crews couldn't restore power from the substation because the hardware between the substation and the customer was physically destroyed. Rebuilding that hardware requires linemen. It requires trucks. It requires replacement poles that have to be transported to each location, set in holes dug in the ground, and strung with new wire. In a normal outage, a localized thunderstorm that takes down 5 poles along one street, a single crew can restore service to several hundred customers in a day. In a serial derecho aftermath, with 10,000 pole failures spread across a service territory the size of eastern Iowa, the math stops working. There are not enough crews, not enough equipment, not enough poles in inventory. Iowa utilities had mutual aid agreements in place to bring in crews from other states. Those crews arrived, but even with mutual aid, restoration in the hardest hit areas took 2 weeks. The power grid, built to specification, maintained to specification, operated by utilities that followed every standard in the book, could not withstand what an 800-mile wall of straight-line winds delivered in 14 hours. The August 10th, 2020 derecho did not arrive in a vacuum. It arrived at the peak of summer, and the connection between the derecho's aftermath and what came next in the days following the storm is the compound threat that the straight damage statistics do not fully capture. Cedar Rapids, in early August, before the storm, was experiencing temperatures in the mid-80s Fahrenheit, normal for Iowa in August, the kind of heat that with air conditioning functioning is entirely manageable, the kind of heat that with air conditioning not functioning, because 2 million customers have lost power, becomes a public health emergency within 48 hours. The elderly and chronically ill are most vulnerable. Many of them live in the kinds of aging housing stock that loses interior temperature fastest: apartments with poor insulation, small homes built before modern efficiency standards. Within 24 hours of losing power, interior temperatures in those structures in Cedar Rapids were climbing into the low 90s. Within 48 hours, some units were measuring above 95 degrees Fahrenheit indoors, particularly on upper floors where heat accumulates. Iowa emergency management officials activated cooling centers across the region. But the cooling centers required power to operate. The cooling centers that were open were concentrated in the areas of the grid that had already been restored. Many of the residents who most needed them, the elderly, the disabled, those without transportation, were in the neighborhoods most severely damaged, where power restoration was farthest away. This is the compound threat hidden inside the derecho's aftermath. The storm doesn't just damage, it disables the very infrastructure needed to respond to the damage. It takes out the power that would run the fans, the refrigerators keeping medication cold, the equipment needed by home-dependent medical patients. It takes out the cell towers that would let people call for help. It takes out the traffic signals that would let emergency vehicles navigate the city. And it does this to every county in the damage path simultaneously. Not to one neighborhood, not to one city, but to a 100-mile wide corridor of 700 miles of American territory. The 2012 Mid-Atlantic derecho illustrated this compound failure with devastating clarity after the June 29th event knocked out power to 4.2 million customers across 11 states and Washington, D.C. Temperatures in the affected region climbed above 100 degrees Fahrenheit for multiple consecutive days. The combination of heat and no power was responsible for a death toll that extended well beyond the storm's direct fatalities. In the Washington, D.C. area alone, where power restoration took up to 11 days. In some communities, the combination of heat and darkness created conditions that emergency managers described as equivalent to a slow-moving mass casualty event.
The atmospheric physics that produces the serial derecho, high CAPE from Gulf moisture, strong low-level jet, summer heating, is the same physics that produces the extreme heat that follows it. The derecho and the heat are not separate threats. They are sequential manifestations of the same atmospheric pattern. The frontal passage that triggers the derecho eventually brings cooler air to the region, but the cooling happens over days, not hours. And in those hours and days immediately following the storm, when the grid is down and the infrastructure is destroyed, and the crews are trying to figure out where to start, the heat is already building inside 10,000 darkened homes.
The National Weather Service has made remarkable strides in the prediction and warning of severe convective events over the past 3 decades. The investment in the NEXRAD radar network, the GOES East and GOES West geostationary satellite series, the Operational High Resolution Rapid Refresh Model, the HRRR, and the deep institutional knowledge of the Storm Prediction Center in Norman, Oklahoma, have pushed severe weather warning lead times to levels that were unimaginable in the 1980s. The median tornado warning lead time in the United States is approximately 13 minutes. That number represents enormous progress from the 0 to 2 minute warning lead, times that were common before the NEXRAD network was complete. The Storm Prediction Center's convective outlooks, which categorize severe weather risk up to 8 days in advance, have measurable skill in identifying the days and regions where organized severe weather is most likely. But for serial derecho specifically, for the 800-mile wall event, the warning architecture has a structural weakness that is not about the skill of the forecasters. It is about the nature of what is being warned for. A tornado warning is issued for a specific location for a specific time period, typically 20 to 30 minutes, based on a radar-identified rotation. It is geographically precise. It is temporally bounded. The message is this specific location in the next 20 minutes has a confirmed or strongly implied tornado threat. A severe thunderstorm warning under current National Weather Service warning criteria is issued when a thunderstorm is capable of producing winds of 58 miles per hour or larger hail of 1-inch diameter. The wind threshold is 58 miles per hour. The severe thunderstorm warning issued for areas in the path of the August 10th, 2020 derecho was technically accurate. The winds it warned about were going to arrive, but the gap between severe thunderstorm warning, 58 miles per hour winds possible, and the rear inflow jet of a serial derecho is going to deliver 140 miles per hour, straight line winds to your neighborhood in 15 minutes, is the gap where lives and infrastructure are lost. The National Weather Service in recent years has developed what it calls a particularly dangerous situation, Severe Thunderstorm Watch, a PDS watch, specifically to communicate when a severe thunderstorm threat significantly exceeds the normal warning threshold. A PDS Severe Thunderstorm Watch communicates that unusually destructive winds or extremely large hail are possible. This is a meaningful communication improvement, but it still operates within the framework of a watch, a large area advisory issued hours in advance, rather than a warning with the geographic precision and urgency that people associate with immediate threat. The high-resolution rapid refresh model, which updates every hour and provides forecasts at 3-kilometer horizontal resolution, has become an important tool for anticipating the development and intensification of bow echoes. HRRR data can show forecasters where the cold pool is deepening, where the rear inflow jet is strengthening, where the system is likely to produce its most intense surface winds over the next several hours. This is genuinely useful operationally, but the mesovortices, those embedded circulations along the leading edge of the bow, echoes that generate the most extreme and concentrated damage, cannot be predicted with precision hours in advance. Their formation depends on processes at the kilometer scale, and even the highest resolution operational models are running at 3-kilometer grid spacing, which means the mesovortex itself is sub-grid scale. It is happening in the gap between the model's data points, invisible to the model's direct diagnosis. The NWS uses radar-based detection of mesovortex signatures, specifically the velocity couplets on NEXRAD, to identify developing mesovortices and issue tornado warnings in their path. But those warnings are issued in real time, based on radar data that is 4 to 5 minutes old by the time it reaches the forecaster's workstation, and the mesovortex may be moving at 55 miles per hour. By the time the tornado warning is issued, the mesovortex is already 1 to 3 miles closer to the area it will damage. This is not a failure of the forecasting system. It is an expression of the physical limits of what can be predicted when the most dangerous element of the storm is generated by processes that operate at scales smaller than any current operational model can resolve. The warning gap for the serial derecho is not a gap between what we know and what institutions are telling us. It is a gap between what physics allows us to predict and what physics actually does. The statistics of power outage, millions of customers, days without power, are useful for conveying scale. They don't convey experience, and understanding why the serial derecho threat is qualitatively different from other severe weather threats requires understanding what extended power loss actually means for the 20 or 30 million people who live in the typical damage corridor. The first 12 hours after the storm passes feel, for most people, manageable. There's a kind of adrenaline from the storm itself, a community energy that comes from neighbors checking on each other and surveying the damage. Phones still work on their battery reserves. Emergency generators at grocery stores and gas stations keep a limited number of locations functional. At the 24-hour mark, the picture changes. The phone's battery is approaching zero, and there's no way to charge it. The refrigerator has been warm for a day. The food is questionable, but not yet certainly unsafe. The freezer, if it has been kept sealed, is still cold enough to be safe. It is summer. The interior of the house is starting to warm above outdoor temperature. At 48 hours, the food safety calculus becomes serious. The refrigerator contents are lost. The freezer contents are beginning to thaw. Prescription medications that require refrigeration, insulin, certain biologics, many pediatric medications, have been at unsafe temperatures for 24 hours. The house interior is now above 90 degrees Fahrenheit. At 72 hours, the water supply is beginning to show stress. Municipal water systems require electric pumps to maintain distribution pressure and to run the treatment systems that make the water safe. Systems that have backup generators can sustain operations for several days. Systems that don't, and many smaller municipal systems across the rural Midwest do not, are starting to issue boil water advisories. Cell networks, which have typically 12 to 24 hours of battery backup at tower sites, are now largely down in the hardest hit areas. At the 1-week mark, which is where the most severely affected customers in Cedar Rapids after August 10th, 2020, were still sitting. The situation has moved from emergency into something that resembles the logistics of a natural disaster recovery operation. Refrigerated food storage for an entire household, safe water procurement, the management of heat stress for elderly or medically vulnerable family members, the sourcing of ice, propane, generator fuel. The basic infrastructure of modern life, which is entirely dependent on electricity, has been dismantled. And this is happening simultaneously across the entire damaged corridor. The disaster that overwhelmed Cedar Rapids, Iowa, in August 2020 was happening, in parallel and at the same moment in dozens of communities across a 700-mile tract. Each community had its own overwhelmed utility restoration crew. Each community had its own food security crisis. Each community had its own medical vulnerability cases. Each community needed the same resources from the same finite supply. The FEMA surge capacity model is built around localized disasters. A hurricane strikes a coastal region. Federal resources flow inward from surrounding states. A tornado devastates a town. State and federal resources mobilize from outside the impact zone. Those models assume that the surrounding region is functional and capable of providing the surge of personnel, equipment, and supplies needed by the impacted area. A serial derecho impact zone is the same width as multiple state boundaries and hundreds of miles long. The surrounding region is inside the damage path. The mutual aid agreements that utilities depend on to bring in out-of-state repair crews require that those out-of-state crews drive through or around the damage corridor. In the August 2020 event, road closures from fallen trees and downed power lines significantly slowed the initial arrival of mutual aid crews to the most severely damaged areas. The infrastructure of disaster response is itself vulnerable to the scale of what a serial derecho delivers. The 850,000 acres of Iowa crops that were a complete loss in August 2020 represent roughly $3.5 billion in agricultural damage from that event alone. But the agricultural dimension of a major serial derecho extends beyond the immediate crop loss in ways that shape rural communities for years. The corn that was destroyed on August 10, 2020, was at the dough stage of development, close to maturity, with the grain filling completed and the plant standing tall. At that stage, corn is particularly vulnerable to wind damage because the stalks are tall and heavy, and the root systems, which have been directing their energy into grain, fill rather than structural reinforcement, are at their weakest relative to the plant's center of gravity. When the rear inflow jet of the derecho arrived at a cornfield, a field that might represent the entire year's income for the farming family that planted it, the corn didn't just fall down, it was slammed flat. Satellite imagery taken in the days following August 10th showed the damage scars across central and eastern Iowa as lighter colored swaths visible from space. Entire sections of landscape where the green of standing corn had been replaced by the dull, brownish gray of flattened, broken stalks. The USDA's remote sensing analysts used those satellite images to quantify the damage, 850,000 acres of confirmed crop destruction. But corn is only part of the agricultural story. The grain storage infrastructure, the grain bins and elevators that hold the output of Iowa's farm operations from harvest through sale, is built to withstand typical wind loads. It is not built to withstand 140 miles per hour straight-line winds. Photographs from the days after the August 10th event showed grain bins across Benton County, Tama County, and Jones County, twisted into shapes that looked more like modern sculpture than agricultural infrastructure. At the Heartland Cooperative Grain Elevator in Malcolm, Iowa, storage bins had been crumpled like aluminum cans. The economic ripple from that destruction extended well beyond the immediate loss. Farmers who lost both their crop and their on-farm storage capacity were simultaneously deprived of their income and their ability to store or sell what they did have. The commodity markets absorbed the shock. Insurance claims flooded into the federal crop insurance programs. USDA emergency loan programs were activated. The machine of agricultural disaster response engaged. But the trees that took down fences, the fences that let livestock out, the livestock that had to be recovered from across multiple counties, those losses don't make the statistics. The semi-trucks that were overturned on Interstate 380, the farm equipment that was destroyed in machine sheds with roofs blown off, the grain dryers that couldn't be operated because there was no electricity, the agricultural disruption from a serial derecho reaches into every corner of a rural economy in ways that cannot be fully captured by any single damage estimate. The historical record of serial derechos across the Corn Belt reads as a periodic disruption of the agricultural calendar, an irregular but recurring economic shock delivered by the same atmospheric machinery, along the same geographic corridor, during the same weeks of summer when the crop is most vulnerable and the atmospheric setup most favorable. The question that follows from the August 2020 benchmark event and from the historical record of serial derecho damage to the electrical grid is whether the grid can be made more resilient to this specific threat, not resilient to all threats, specifically resilient to the kind of broad area, extreme, straight-line wind event that serial derechos deliver. The honest answer from grid engineers and utility infrastructure researchers is yes, technically, but the economics are prohibitive at scale. Underground power distribution, bearing the distribution lines that currently run on poles along every street, is the most complete solution. Underground lines are not exposed to wind. They don't fall trees. They don't snap poles. They don't create arc flash hazards during extreme weather. The physics of underground distribution are well understood, and it is widely deployed in new residential developments where the trenching cost can be amortized into the development budget. Retrofitting existing overhead distribution to underground is a different calculation entirely. The Penn State Institute for Energy and the Environment estimated in 2025 that the cost of undergrounding all distribution infrastructure in a typical northeastern state would run into the tens of billions of dollars. For a Midwestern state with a large rural service territory, Iowa for instance, the cost would be similar or higher per customer because the distribution lines cover greater distances with fewer customers per mile. That cost is real. It is not being dismissed, but it has to be weighed against a different number, the $11.2 billion of damage caused by a single derecho event in August 2020. If a state experiences one August 2020 scale event per decade, and the historical record suggests that's a plausible frequency for major events in the high-risk corridor, then 10 years of not undergrounding is an expectation more expensive than 10 years of undergrounding. That calculation is too simple in several ways. Not all damage is grid damage. Not all grid damage is avoidable through undergrounding. Underground systems have their own failure modes in floods. The financing of a multi-decade undergrounding program creates regulatory and capital structure challenges that utility commissions have not fully solved. But the grid hardening conversation is happening. The Infrastructure Investment and Jobs Act of 2021 included provisions for grid resilience investments, and the Department of Energy's Grid Resilience and Innovation Partnerships Program, GRIP, has allocated funding specifically for hardening distribution infrastructure against severe weather. Utilities in the states most regularly affected by derecho events have filed grid hardening plans with their state regulatory commissions. The conversation is active.
What has changed since August 2020 is the reference point. Before that event, a utility making the case for undergrounding a particularly vulnerable section of its distribution network had to argue from historical precedent and model probabilities. After August 2020, the argument can point to $11 billion of documented damage and 2 weeks of darkness for nearly 2 million customers and say, this is what the system produced in the absence of hardening. The reference point is now concrete rather than theoretical.
The meteorological research community has been actively working on the problem of serial derecho prediction for decades, and the progress is real even if the fundamental physical limits described in Part 10 remain in place. Understanding where the science is moving is important for assessing what the future warning landscape for these events looks like. The HRRR model, the high-resolution rapid refresh, has been the operational workhorse for short-range convective forecasting in the United States. At 3-kilometer horizontal resolution, updated every hour, it has demonstrably improved forecasters' ability to anticipate where bow echoes will develop and intensify. The National Severe Storms Laboratory and NOAA's Earth System Research Laboratory have been working on next-generation ensemble convection-allowing models, CAMs, that run at 1 to 2 kilometer resolution across multiple ensemble members simultaneously, providing both higher resolution and probabilistic guidance about where the uncertainty is greatest. The value of ensemble cams for derecho forecasting is not in predicting exactly where the mesovortex will touch down. It is in quantifying the probability that the atmospheric environment is favorable enough for an extreme event. When 10 out of 10 ensemble members show a large bow, echo, developing over the same region at the same time, the forecaster has high confidence in the basic scenario, even if the specific track and intensity remain uncertain. The research community has also been investing in improved understanding of the rear inflow jet dynamics. The Baymax Field campaign in 2003 generated a detailed data set of airborne Doppler radar observations of bow echoes that has informed the development of new theoretical frameworks for rear inflow jet strength prediction. Models that better represent the diabatic processes, the cooling from evaporation and melting of precipitation within the stratiform region, are more skillful at predicting when the rear inflow jet will become particularly intense. Dual polarization radar, now standard across the entire NEXRAD network since the upgrade completed in 2013, has added an additional dimension to the real-time diagnosis of severe convective systems. Dual polarization variables, particularly the correlation coefficient and differential reflectivity, can identify hail, large raindrops, and debris within the storm with much higher confidence than single polarization radar. For derecho events, the dual pole radar data helps forecasters identify the leading edge of the cold pool and the gust front, providing a better real-time picture of where the most dangerous winds are occurring. The National Weather Service's Warning Decision Training Division has developed specific training curricula for forecasters on derecho recognition and warning strategies. That training includes guidance on when to use enhanced severe thunderstorm warning language, including the particularly dangerous situation designation, and how to communicate the extreme wind potential of a serial derecho event to emergency managers and the public in language that conveys the severity of the threat without triggering the paralysis of information overload. The communication research is, in some ways, as important as the meteorological research. Studies of public response to severe weather warnings have consistently shown that people are more likely to take protective action when they understand what specific threat is approaching, what specific consequences it will produce, and what specific action they should take. A warning that says, "Severe thunderstorm warning, winds to 80 miles per hour, take shelter immediately," produces better behavioral response than one that says, "Severe thunderstorm warning in effect until 5 o'clock p.m." The warning communication challenge for the serial derecho is that the appropriate protective action is different from, and in some ways more complex than, tornado protection. For a tornado, the message is simple: get to the lowest level of the most solid structure available. For a serial derecho, the immediate life safety threat is still best addressed by interior shelter, away from windows. But the compound threat, the grid failure, the heat, the extended outage, requires preparation that cannot happen in the 15-minute warning window. It requires the kind of household emergency preparedness that public communication campaigns have been trying to instill for decades with mixed success. The evidence assembled across this investigation points to a specific kind of threat. Well documented, historically recurring, increasingly well understood by the meteorological research community, and consistently underestimated by the public, it regularly endangers. But how we interpret that evidence depends on which framing we bring to it. The first interpretation is the most reassuring, and it deserves to be stated fairly. The argument runs like this: serial derecho events of the August 2020 magnitude are statistically rare. Ashley and Moat's climatology established approximately 21 derecho events annually across the United States, and the overwhelming majority of them produce damage in the tens to low hundreds of millions of dollars. Serious, but not catastrophic at a regional scale. The August 2020 event was a genuine outlier, far out in the tail of the historical distribution. The National Weather Service, despite the warning lead time limitations described in Part 10, did issue watches and warnings for the August 2020 event that gave people who were paying attention meaningful time to seek shelter. The death toll from a 14-hour, $11 billion event was 4. That is a testament to both the warning system and a public protective response. The grid failed, but it was repaired. Cedar Rapids lost its tree canopy, but the city has embarked on a systematic relief program and is rebuilding. Infrastructure fails in natural disasters. That is why we have insurance, mutual aid agreements, and federal disaster response programs. The system worked imperfectly, but it worked. This interpretation is not wrong. It is fair. It accounts for the actual data. The second interpretation is intermediate and reflects where much of the technical community's thinking sits. It goes like this. The August 2020 event was a statistical outlier, but not an impossible one. The atmospheric setup that produced it, the specific combination of high Cape, strong Gulf moisture advection, fast-moving cold front, and favorable upper-level pattern, occurs multiple times per decade in the high-risk corridor from the central Great Plains through the upper Midwest and Ohio Valley. The August 2020 event was the worst on record because it hit in the right place at the right time with the right intensity. But a dozen prior events have produced damage in the hundreds of millions to low billions. The trajectory of the historical record is not one of isolated extraordinary events. It is a distribution of events with an extreme tail that has been sampled twice in the last 15 years. The 2012 Mid-Atlantic event and the 2020 Midwest event. The infrastructure vulnerability documented in both events is real, persistent, and not adequately addressed by the investments made to date. The warning system improvements are meaningful, but cannot close the warning gap for mesovortex scale phenomena. This interpretation says the system is managing a known risk inadequately, the risk is recurring, and the investments needed to better manage it are being made too slowly. The third interpretation takes the evidence in its full weight and draws the most concerning conclusions. It argues that the combination of factors driving the severity of these events is not static. The Gulf of Mexico is warmer than it has been at any point in the instrumental record. Warmer sea surface temperatures increase the amount of moisture available for transport northward by the low-level jet. More moisture in the warm sector ahead of the cold front means higher Cape values. Higher Cape values mean more energy available to the convective system and more potential for extreme winds through the cold pool and rear inflow jet dynamics. Research from multiple institutions has found statistically significant trends in the frequency and intensity of extreme precipitation events across the Midwest. The same region where serial derechos draw their moisture. If the atmospheric moisture loading is increasing, and if that moisture loading is the primary energetic driver of serial derecho intensity, then the historical distribution of event severities is a sample from a distribution that is shifting toward higher extremes. The next August 2020 may not be an outlier from the historical distribution. It may be representative of the new distribution. Only continued observation, research, and the accumulation of additional extreme events, a body of evidence none of us should want to acquire, will establish which of these three interpretations best describes reality. There is a specific moment in an August 20th, 2020 type event that is worth dwelling on, because it captures the warning gap with concrete precision. At approximately 11:45 in the morning on August 10th, 2020, the Storm Prediction Center's mesoscale discussion, a real-time analysis product issued when significant convective events are imminent or occurring, described a derecho-producing bow echo moving rapidly east-northeast across central Iowa with estimated surface wind gusts of 70 to 100 miles per hour, and noted that winds of 100 mph or greater were possible where the rear inflow jet was most intense. At that moment, Cedar Rapids, a city of 140,000 people, was 40 to 50 miles ahead of the most intense portion of the storm. At the system's forward speed of approximately 55 miles per hour, Cedar Rapids was 45 to 55 minutes from the storm's arrival. What do you do with 50 minutes? If you know the storm is coming and you understand what it is, 50 minutes is meaningful. You can move your car to a garage. You can get your family into an interior room away from windows. You can charge your phone to full power. You can fill your bathtub with water. You can take your medication out of the refrigerator if it needs to stay at temperature and put it in an ice chest. You can get a flashlight. But 50 minutes was not the effective warning lead time for most of the 140,000 people in Cedar Rapids on the morning of August 10, 2020. The mesoscale discussion is a product issued for meteorologists and emergency managers. It is not a push notification to every phone in the warning area. The National Weather Service had issued a tornado watch for Iowa at around 9:15 that morning. There were severe thunderstorm warnings and tornado warnings issued as the system approached, but the behavioral research on public response to severe weather warnings consistently shows that a substantial fraction of the public does not receive, process, or act on severe weather watch products until the warning, the higher urgency product, is issued. And for many locations in the Cedar Rapids metropolitan area, the gap between the first severe thunderstorm warning and the storm's arrival was 15 minutes or less. 15 minutes is enough time to move away from windows. It is not enough time to fill your car with gas, gather emergency supplies, charge your phone, or do any of the preparatory actions that would meaningfully reduce the impact of a 2-week power outage. The warning gap for the serial derecho is real. It is a product of physics, not negligence, and it makes the pre-event preparedness of individual households the kind of preparedness that emergency management agencies advocate, but that most households don't maintain, more consequential for outcomes than any improvement in the warning system can fully compensate for. Strip away all the analytical framing, and this is what the evidence actually shows. A serial derecho, a quasi-linear convective system, generating multiple bow echoes and rear inflow jets along an 800-mile continuous line, is physically capable of producing 100 to 140 miles per hour straight line winds across a 100-mile wide corridor that spans multiple states simultaneously. The August 10th, 2020 event documented this capability with $11.2 billion of evidence, 770 miles of documented damage, 1.9 million customer outages, 2.67 million damaged or destroyed trees, 850,000 acres of destroyed crops, and 4 deaths. The atmospheric conditions that produce these events, high CAPE from Gulf moisture, strong wind shear, fast-moving cold fronts, favorable upper-level patterns, occur multiple times per year over the high-risk corridor of the central and eastern United States. The National Weather Service warning system provides meaningful watch and warning lead times for these events at the regional and county scale, but cannot provide precise warning with adequate lead time for the embedded mesovortex features that generate the most extreme concentrated damage. The electrical distribution grid across the high-risk corridor was not designed to withstand the extreme tail of the wind distribution produced by mature serial derechos, and grid hardening investments that would address this vulnerability are being made at a rate insufficient to close the gap before the next major event. The compound threat, the interaction between the derecho's grid damage and the heat that follows, is the mechanism by which a storm that kills 4 people directly can produce cascading health and safety consequences for millions of people over the following 2 weeks. The research community is making real progress in understanding the dynamics of the rear inflow jet, mesovortex formation, and the large-scale environments that produce the most intense events. The operational forecasting system has improved meaningfully since the NEXRAD network was completed in the 1990s. Dual polarization radar, ensemble convection allowing models, and improved warning communication protocols have all contributed to a better warning landscape. What the data does not show is that the system is adequately prepared for the next August 2020 event, or for an event that exceeds it. The wall doesn't care about the calendar. It doesn't wait for infrastructure upgrades or warning system improvements or household preparedness campaigns to reach their target completion dates. It forms when the cold front moves at the right speed and the Gulf moisture is in place, and the shear profile aligns and the instability reaches the threshold. And when it forms, it crosses the country in an afternoon. What the August 10th, 2020 event left behind was not just $11 billion of damage and 770 miles of debris. It left behind a reference point, a benchmark against which every subsequent discussion of grid resilience, of warning communication, of agricultural vulnerability, of emergency preparedness has to be measured. Meteorologist Alan Curtis of the National Weather Service told reporters after the event that the derecho caused such extensive damage because it lasted for roughly 14 hours and hit the crops and the grid at the moment of maximum vulnerability. That observation, maximum vulnerability, precisely timed, is the key to everything. The atmospheric machinery doesn't time its strikes for convenience. It operates on the logic of thermodynamic potential, and that potential peaks in the same weeks of summer over the same geographic corridor, with the same underlying ingredients year after year. The system that produced August 2020 existed in the record before August 2020. The June 29th, 2012 event was there. The April 4th, 2011 event was there. The June 30th, 2014 event was there. The line keeps moving. What changes is the reference point. After 2012, the benchmark was 4.2 million customers in the dark across 11 states. After 2020, it was $11 billion. After the next event at or beyond that magnitude, the benchmark will shift again. Whether it shifts in the direction of worse outcomes or better managed outcomes depends on the investments made in the interval. In grid hardening, in warning communication, in household preparedness, in the research infrastructure that is pushing the forecasting skill of these events forward. The science is clear about what these storms are. It is clear about what they do. It is clear about where they are most likely to form, when they are most likely to occur, and what conditions make them most severe. What it cannot tell us, what no amount of modeling can tell us, is which warm sector, in which June or July or August, carrying exactly how much cape from the Gulf, will be the one that produces the next benchmark event.
We will be watching. We will be tracking the HER output and the Storm Prediction Center outlooks and the NextRad Velocity products as each severe weather season develops. And when the wall forms again, the continuous 800-mile line of rear inflow jets and bow echoes racing east at highway speed, we will be here. Drop a comment below and tell us, do you live in the derecho corridor? Have you been through one of these events? We want to hear your story. Like and subscribe to Signal Watch so you're with us for the next investigation. The line keeps moving, and so do we.